Okay, so in this lecture we are going to talk about the very important topic of simulating data. Now, why would you want to simulate data? Well, the main purpose of simulation is going to be to understand the statistical power properties of our experiment design. And why would we want to do that? Well, first of all, we will typically want to do a power analysis before we run the experiment, in order to decide on the sample size that we will need to have adequate power. So if you remember, we had done in a previous lecture, so lecture 3, we had talked about statistical power, which is the probability of your correctly rejecting the null hypothesis. That means when the null hypothesis is actually false, what's the with some particular value, what is the probability that you will reject that null hypothesis, right? So that power needs to be high, because if power is high, then type 2 error is low, and we want to keep type 2 error low. Type 2 error, if you remember, is the probability of failing to reject the null when the null is actually false with some particular value. Okay, so you want to keep this type 2 error low. This 1 minus beta is power, and we want to keep that high, and so we want to set up a design such that we have as high a power as possible. So for that we will need simulation, because we will have very complicated experiment designs with repeated measurements, and simple power.t.test functions can give you an approximation, as I will show you, but they can't really give you reliable estimates of power in your particular design. Okay, another reason why you want to simulate data once you've done an experiment, the experiment is done, you may still want to study the power properties of your experimental data for a future experiment, and in doing so understand whether you are in a type M error situation. So suppose you do an experiment and you get a significant result. That sounds exciting, but what would happen if you ran that experiment many times with some reasonable value for the effect size? If you're unlikely to detect that effect again, then that's a strong indication that you have an accidental type M error situation. Okay, so these are ways to think about your result, going beyond the simple p-value diagnostic. So to understand the power properties is crucial when you do an experiment. Another reason you want to do simulation is to understand which parameters you can recover in principle, under hypothetical repeated sampling. So you repeatedly generate simulated data, and you draw the distribution of each of the parameters that you estimate in each time you fit the model. I will just show you an example, of course, and this will help you understand whether your model makes sense at all or not, right? Whether it can recover the parameters or not. So I will show an example. So we will start by looking at a very simple scenario between subjects design. The purpose of this simple scenario is to just get you into the flow of doing simulations. In practice, I never use between subjects simulations, because I never have between subjects designs, or almost never. I usually have within subjects designs. So once I prepare you with a between subjects design simulation, then I will switch to the within subjects design and show you how you can generate data that we would typically analyze using a linear mixed model. Okay, so let's start with a simple case. So suppose we have reading time data in milliseconds from 10 subjects, and these subjects see subject relative clauses. Okay, and we have a different set of 10 subjects who see object relative clauses, right? So each subject has seen either a subject relative clause or an object relative clause, but not both, and we have a total of 20 subjects, right? So we're going to assume that standard deviation, so the residual standard deviation is 300, the true subject relative reading time is 700, and the true object relative reading time is 750. Okay, so the true difference between the subject and object relatives is 50 milliseconds, right? So how to simulate this kind of data, right? So we're going to generate hypothetical data under these assumptions of each of these parameter values. Okay, residual standard deviation 300, subject relative reading time 700, object relative reading time 750. Okay, so what we're going to do is we take 10 samples from the subject relative normal distribution. So we assume that the normal distribution is generating the data. We could have assumed something else, like log normal or gamma or something, but in this course we just keep it simple. And for the object relative, we simulate 10 data points coming from normal distribution with this mean and standard deviation. And then we just create a data frame with the appropriate subject ID. Okay, so how do we do that? So let's do this. For subject relatives, I generate 10 data points from this distribution. For object relatives, 10 data points from this distribution. And now I create a vector going from 1 to 20. And I create a column called cond for condition, which has 10 instances of subject relatives and 10 of object relatives. So that's what this command does. And now I just created a simulated data frame called simdat. That is, a data frame has a column called subject, and this sub is a vector going from 1 to 20, has the condition column which has 10 instances of subject relatives, 10 instances of object relatives, and the concatenated vector of SROR reading times that we just generated here. So this is all simulated data now. We just generated our first simulated data set. Okay. So now the interesting question is, how can I generalize this? How can I repeatedly generate such data, right? So I could do this again and again, what I've just done here, but there's a better way to do this, and the better way is to write a function. So we're going to write a function that for a particular sample size in each condition, that's what that n refers to. I want to remind you of homework 1 there, right? And the mean for the first condition is this, the mean for the second condition is this one here, the standard deviation is here. So these are all the parameters that go in this function, and this will generate, this function called between subject simulated data is going to generate now n data points for subject relatives, n data points for object relatives, create a vector going from 1 to 2 times n, right? So if n is 10, then it will be 20, and then create the condition factor with n replications of SR and n replications of OR. That's what this command does, and wrap it inside factors so that these are considered to be factors and not strings. Okay. And now we just create a data frame with the subject column, condition column, and the reading times. Okay, so now, and then it prints out the data frame. So what this function does is, you can just take the default values if you want to generate 10 data points with the given parameter values that are the default values here. You can generate data repeatedly now. So here, what I'm going to do, what this for loop will do is 100 times it will generate a completely new fake data set, simulated data set, using the parameter settings that I gave it. Okay. So now, why would I want to generate repeated data like this? The reason is that I can use this now to do power analysis and to check if the model recovers the parameters correctly. This is what I mentioned earlier. Okay, so let's take a look at how this works. First of all, I want to remind you of the power.t.test function that we used, I think, in homework 1. So imagine that the difference between the two means is 50 milliseconds. We have a sample size of 10 in each condition and a standard deviation of 300. It's a 2-sample experiment and it's a 2-sided t-test. Okay, so we're going to do the t-test and compute power here, and when I compute power to 3 decimal places, I get a power of 0.064. Okay, I'm going to now do the same power analysis. I'm going to compute power using simulation, by simulating data repeatedly. Okay, and you will see that I'll get a very similar number. Okay, so let's say I simulate 100,000 times the following. Okay, I'm going to run 100,000 simulations in this for loop. Each time I'm going to generate a simulated data set using my built-in function, not my built-in function, but using my handcrafted function. And once I have the simulated data, and you remember what it looks like, something like this. So I'm going to have RT as a function of condition in a between subjects design. So I'm going to say t.test RT as a function of condition, paired equal to false. Why? Because it's a between subjects design. give the data frame as an input to the t.test function, and extract the t value, right? And save the t value in a vector that we create before we start the simulation. We create this vector observed t values with 100,000 empty cells, and each time this for loop runs 100,000 times, the ith cell of this vector observed t will be saved in this vector. And so we can use that vector, this observed t vector, we can compute the absolute value of this thing and then find out what proportion of these observed t values, the absolute observed t values, exceed the critical t value, the absolute critical t value, right? And that number, the proportion of cases of the observed t value that exceeds the critical t value, of course the absolute values, will be the statistical power, right? So in this case, power is 0.06, which is pretty much the same number that we got here. Okay, so what I'm showing you here is that for these simple designs, you can either use the analytical approach of the power.t.test function, or you can just use simulation. You know, you'll get pretty similar conclusions. Okay, so next what we're going to do is we're going to learn how to compute power using simulation in between subjects designs, but this time we're going to use the linear modeling framework. We're not going to use the t-test, right? So in this case I was using the t-test, but we're going to use this time the linear model. Okay, all right, so then after that, once we've done that, we'll learn how to compute power for within subjects design using t-test and Elmer. Okay, so first of all, the default contrast coding that I'm using here is of course the treatment contrast, because I didn't mess around with the contrast coding yet for SR and OR, right? And OR is coded as 0 and SR is 1 because of the alphabetical ordering here. O comes before S, that's why. That's the only reason. Okay, anyway, so now we do our usual thing, which is to recode our contrast as some contrast. So I've just redefined the contrast coding as some contrast, and now I've got OR is +1, SR is -1. The method I prefer, of course, is this one, where I use the if-else function to code the OR is +1 and the other condition is -1. Notice that I'm not using any NA or anything like that here for any other situation, right? So there are only two conditions. So I just, because I have only two conditions, I know that. So for one I have +1, for the other one I have -1, and so I create a new vector called RC type, which is going to be my predictor now. Okay, so I mean I could do that, but I'm going to use cond just to be consistent with the story right now. Okay, so now in this two sample t-test and ANOVA, and I showed you earlier that the two sample t-test, ANOVA, that is the likelihood ratio test, and the linear model are all exactly the same thing. Okay, so let me just remind you of this thing. So when I do this t-test with RT as a function of condition in a between subjects design, and I extract the t statistic, I get -2.444. okay, if I do a linear model on the same data and extract the ANOVA, I get an F score of 5.97. Now if you remember, F is equal to is the same thing as t squared, right? So if I take the square root of the F, I'm going to get the t value, which is exactly 2.444. okay, so well, very close to 2.444. So, and similarly, like if I do the linear model and I look at the t value in the linear model, lo and behold, I again get the same t value, right? So the t-test, ANOVA, linear model, they're all the same thing basically, right? Not basically, they are the same thing. All right, so now how to do simulation using the linear modeling framework. So we're going to write the linear model as follows. For every row I in the data frame that we have, the reading time called RT is going to be generated from a model where the contrast coding of the condition column in the ith row of the data frame is going to be coded +1 or -1. Okay, depending on whether we are looking at whether the row contains a subject relative or an object relative clause data point. Okay, so just to go back here, so whenever if the first row has SR, it'll be coded as -1. and if any further row has an OR, it will be coded as +1, right? That is what we are doing here, right? And we are going to assume that there's Gaussian noise on the residual noise is there. Okay, for every data point there will be some residual noise coming from this normal distribution with mean 0, standard deviation 300. Okay, so we've set up a linear model generative process now, where we say that every ith row of the data frame is generated from this model. Okay, so what that means is that we'll be computing this quantity with this coded as +1 or -1 depending on what's in the ith row of the data frame, and we'll have some random number, one random number that we'll have produced from this normal distribution in the ith row. Okay, so what we will have is for the first 10 rows of the data frame we have only subject relatives which are coded as -1, and for the second 10 rows we have object relatives which are coded as +1. Okay, so what the data frame looks like in matrix form is like this. Okay, what we have is 20 rows. Okay, and the intercept is always 725. Remember, I'm just using the multiplied by 1 here because in the design matrix the first column is always 1, right? That's why this one is there. And the second part here that you're seeing, this is the 25 millisecond effect in the +1 -1 coding. The effect size is going to be half that of the case when we have effect coding, right? With 0.5 ±0.5 coding, we would have had to write 50 here, not 25. Okay, so I hope you remember this discussion from the contrast coding lectures. So anyhow, the first 10 rows will have -1 because they are subject relatives. The second 10 rows will have +1 because they are object relatives, and then we'll have some Gaussian noise here. Every number will be different because it's generated from a different, generated afresh from a normal distribution. Just one data point is generated, right? So one residual value is generated. So this is how. So if I compute each of these numbers, these 20 rows of values, I'm going to get some predicted data. Okay, so how do we proceed? Remember that like whenever we do such, so whenever we have such data, we can, once we've generated the simulated data using this kind of a setup, what we can then do is that we can do a hypothesis test in the usual way, the way I have taught you in homework 4, I think, using the ANOVA function and so on. You could even look at the t-value, and look here, the t-value for my simulated data. This is with the simdat function. I had produced that data. You know, the simdat data I had produced, I get the same t-value here, and I get some p-value which you can extract from this command, right? So if you use summary, name of the model, $coefficients, and then the second row, fourth column, that gives you the p-value, right? Because this is the second row, this is the second row, and this is the fourth column, and here's the p-value, right? This is in scientific notation. That's why it looks so funny. It's 2.5 multiplied by 10 to the power of -2, right? And so that exactly corresponds to 0.02, right? Okay, so that's what this extracts for you. It extracts the p-value, and we're going to use that in a moment. Okay, all right. So alternatively, of course, you could do the likelihood ratio test and extract the p-value from that. It's going to be exactly the same number, right? Because these are identical tests. So you can decide whether you want to use the ANOVA or the t-test output, the linear modeling output, to extract the p-value. When you have unbalanced data, right, then you should always be using the ANOVA function and not using the t-value. You should not be using this t-value to decide on significance, you know, if you have missingness in the data. All right, so this is a more general approach. Okay, all right, that was just a side note. But now I'm going to show you how to do a power analysis. The way you would do the power analysis now is that you're going to do a certain number of simulations. So let's say 10,000, and I want to do a large number of simulations just because I can. and I'm going to compute the p-value. I'm going to generate simulated data each time, each of these 10,000 times. I'm going to fit a linear model to the that generate simulated data. I'm going to extract the p-value like I just showed you. I showed you how to extract the p-value. So I'm going to extract the p-value and save it in a vector, right? And then I'm going to check the proportions of times in those 10,000 cases that I had a p-value that was less than 0.05, and that is my statistical power, because that is the proportion of times that I rejected the null hypothesis correctly. Why correctly? Because the true value of the effect is 50 milliseconds, right? That's I had set that up. I had set up the simulation in this way that the null hypothesis was actually false. Alright, so now the question is, how do I do this simulation? So this is an exercise for you right now. So what you must do is you should pause the video and try to write this for loop yourself. Don't jump ahead to the next part of the presentation. Just stop the video and try to follow my instructions here and compute your power. Okay, so I'll continue now, but I'm hoping that you will stop at this point and try to do this for loop yourself. Here's the solution. The solution is that I'm going to create a vector for p-values, storing the p-values with nsim cells which are empty, and then for nsim simulations I'm going to generate between subjects simulated data. I'm going to fit a linear model to that and save it as an object m, and then I'm going to extract the p-value as I showed you earlier and put it into the p-vals vector in the ith cell. And then after the for loop is over, I'm going to check the mean number of times, so the proportion of times that these p-values are below 0.05, and I'm going to print out that result by rounding it to 2 decimal places. And lo and behold, we get a similar answer of 0.06 to the one that we got at the very beginning of this lecture. Okay, so now we can also check whether the model can recover the true parameters under repeated sampling. This is an important check, because what this tells us is that the model, given the kind of assumptions that we have set up, for the generative process of the data. So whenever you fit a model to statistical model to some data, what you're implicitly doing is that you're asserting that you believe that the underlying generative process that produced that data from human beings can be modeled by the equation that you put in Elmer or whatever, right? So that's, you're defining a generative process. So what this simulating, checking whether the parameters can be recovered is an interesting way to check whether the model is valid, in the sense that can the model in principle recover the true parameters under repeated sampling. So what we're going to do is 10,000 times we will run the same thing that I just showed you. We're going to simulate data 10,000 times, fit a model to the simulated data each time, and each time we will extract all the parameters from the model. There are only 3. There's the intercept, slope, and the standard deviation. So what I've done is I've created a matrix called params, which contains 3 times the number of simulations in a 10,000 by 3 matrix. Okay, so in the first column of the matrix I'm going to stick in the intercept, the second column of the matrix I'm going to stick in the slope, and the third column of the matrix params I'm going to stick in the standard deviation. So that's what I've done here. In the ith row of the params matrix, the first 2 columns will be filled by the intercept and slope. That means the first column of the coefficients, right, from the summary output. And right, so you remember what I'm talking about here. So I showed you earlier here, right? So I've got a 2 by 4 matrix here. The first column is the coefficient. This is the coefficients. These are all the coefficients. The first column is this thing here, the intercept and slope. So I'm extracting that in this code here, right? So I've just extracted the first column, okay? And then the third column of the params matrix will be filled with the sigma value, the standard deviation, okay, from each of the simulations. So what I have is 10,000 estimates of the intercept, 10,000 estimates of the slope under repeated sampling, and 10,000 estimates of the standard deviation. Now I also know the true values of these numbers, right? 700, 750, no, sorry, 700, 25, and 300, right? So these are the numbers. So what I've done here is I've plotted the distribution of the intercepts under repeated sampling. I've plotted the distribution of the slopes under repeated sampling and of the sigma under repeated sampling, and the vertical lines that you're hopefully able to see here, these vertical lines are actually the true values. This is 725, this is 25, and this is 300, right? And what you can see is that the model, the distribution of the parameter estimates is centered bang around the true value. That means the model is able to nicely recover the true parameters, right? This is an interesting check, because what this tells us now is that the data generative process we have defined for the data we are analyzing, and of course we are analyzing simulated data, right? So what we are doing is we are generating simulated data because the simulated data expresses our belief about the underlying generative process. Okay, so what this parameter recovery process is telling us is that the model is able to recover these parameters under repeated sampling, and what that means is that it's a generally quite a reliable recovery. How can I say this better? That we can be generally confident that the underlying generative process that we've defined is a reasonable one. Okay, in this case, of course, it's a reasonable one because it's such a simple process, and we actually set up the simulated data ourselves, and then we analyze the simulated data using a known function. We know how the function, what the function was that generated the data, but later on when you look at more complicated cases with repeated measures data, the more abstract parameters, the random intercept standard deviations, the random slope standard deviations, the correlation between intercepts and slopes, you might think that your model is a reasonable one, but you may not be able to recover those parameters under repeated sampling. Okay, so I'll show you an example in a moment, and that shows you that the model, and that will show you that the model that you're trying to fit is too ambitious. So you should back off to a simpler model, because you can't even recover those parameters in principle, right? In the more complex cases. Example is coming up later on when we talk about within subjects designs. Okay, so I just said all this, that parameter recovery tells you the properties of your model under repeated sampling. This is something you can't do in real life, but with simulation you can certainly find out if your model will recover the parameters. Okay, all right, so now the next part of this lecture is about generating within subjects data. Okay, so continuing with the presentation of lecture 6, I'm going to talk in part 2 about generating within subjects data now. So now we suppose, let's assume that we have a total of 10 subjects, That means we have the same subject seeing the subject relative and the object relative once each time. Okay, so each subject is going to deliver 2 data points now, not 1 data point like in the between subjects design. So what's important here is to pay attention to the subject IDs that we will generate when we produce the simulated data, because the same subject ID has to be used for the subject relative exposure for that subject and the object relative exposure. Okay, so we have to repeat the ID twice, right? So how do we do this? We're going to have 10 subjects, like I said, and then we will generate 10 data points for subject relatives coming from this distribution, and 10 data points for object relatives coming from this distribution. And what's important now is that we're going to generate numbers for the subject going from 1 to 10, but we're going to repeat that sequence 1 to 10 twice, right? Because 10 times for subject relatives and 10 times for object relatives. The condition column remains the same, and the data frame that we will now generate has the subject column generated as shown here, then the condition and the simulated data, right? So that's the entire data frame that we generated here contrast coding is shifted to some contrast coding here. And so what we get as a result is numbers going from 1 to 10, and then 1 to 10 repeated again in this case, right? So shall I just do this quickly? Let me see. Yeah, so let's just try this quickly, right? The data, the head of the data looks like this. The first few lines look like this, but let's just draw the full, pull out the full data set. So what you see is the first 10 lines contain the data for subject 1 to 10 for subject relatives, and the next 10 lines contain the data for the same 10 subjects going from 1 to 10. Now, if this was a between subjects design, the subject ID would go from 1 to 20. So you would not repeat the same numbers here. Okay. So this is the first step towards, generating within subjects data. We are not quite there yet, but we'll just get to this, complete this whole process. Okay. So as I just explained, the total number of subjects is n, that is 10, and 2 times n was what we had in the between subjects design, right? 20. So that's what I just explained. Of course, the number of rows in our data frame will be 2 times n, even in the within subjects data, but the number of subjects will be n now. Now, one problem in this data that I've generated is that the within the subject IDs are correct, but the generated data don't really reflect the fact that we have within subjects data. And the reason is that we are incorrectly assuming that the subject and object reading times are being generated independently of each other, and that independent generation is expressed here, right? We've got 2 different normal distributions that we are getting the subject and object relative clause data from. But what is missing here is that we are not taking into account that there is something in common between the subject and object relative clause data point from one given subject, because one subject is generating one data point for subject relatives and object relatives. There is a commonality, there is a dependency between those 2 data points that we are not expressing in the data generation process. So how do we express that dependency, right? I'll explain how that works now. So we're going to start by assuming that each subject has a different true mean processing time. So some subjects will be faster, some subjects will be slower than average. So that that fact has to be expressed somehow, that each subject has a different true mean processing time. And we will use this assumption to induce a dependency, right? So I'll show you how this works in a moment. So one way to encode this assumption of a dependency that each subject has a different processing time is to assume that some subjects have a reading time, a processing time that is faster than the grand mean average of 725, and the others have a mean processing time that is smaller than the grand mean average. And some subjects might have a mean processing time that is the same as or very close to the grand mean processing time. Okay, so we can express this as follows. We can generate adjustments to the grand mean of 725 for each subject by creating a vector of n scores that come from a random variable that has mean 0 and some standard deviation, which I'll assume to be 200 here. Okay, I'm just making up some standard deviation here. So this standard deviation is what we see in the linear mixed model when we compute the standard deviation estimate of the varying intercepts. Okay, so that's that standard deviation that I'm stipulating is 200 here, right? So basically what I've done here in this line is that I'm generating an adjustment to the subject for each subject such that their average processing time is 725 milliseconds plus some adjustment, and that adjustment is generated from this normal distribution. So what you see is that the adjustment is, for example, for one subject is minus 228. That means that for that subject is assumed to be faster than average. okay, because it's 725 minus 228. This subject is considered to be slower than average, and that's because their average processing time is 725 plus 161, right? So slower than average. So these numbers are generated randomly. That means every time I simulate data and simulate adjustments by subject, I'll get different numbers each time. Okay, so there's nothing sacred about this number. It just happens to be an assumption that each subject, so that this subject has a faster than average reading time, right? Okay, if it happens, that we get a value 0 in this vector, and this can happen because the mean is 0 of the generative, distribution. This would imply that that subject's mean reading time is 725 plus 0 milliseconds. That means 725 milliseconds, right? So basically we are expressing the fact that there'll be a grand mean of 725 and different subjects will vary around that grand mean. Okay, their mean processing time will vary. Okay, and so now what I'm showing you here is the subject adjustments added to the grand mean, and so you can see that the first subject's mean processing time is faster than average, and this guy's is slower than average, right? What I just explained. Okay, so what do I do with this new adjustment? What I'm going to do is that I'm going to generate reading times now. So remember that I have a condition vector which is coded -1 plus 1, and I have 10 instances of -1, that is subject relatives, and 10 instances of +1, that is object relatives, and that's why I can write this command, repeat -1 10 times and +1 10 times, right? So that's what this condition vector will look like now. And I can now generate simulated data by taking the grand mean, then taking the subject adjustments repeated twice, because I have subjects 1 to 10 followed by another 1 to 10, right? Remember that in this data I have the first 10 rows are subjects 1 to 10, the second 10 rows are subjects 1 to 10. So whatever the adjustment for subject 1 is will have to be repeated here, right? And for whatever the adjustment for subject 2 is has to be repeated here. So that is why I repeat the subject adjustment twice, so I get the correct adjustment. And then what I'm doing is I'm taking the slope of 25 and multiplying it with this contrast coding of +1 -1, and then adding random noise. I'm adding n times 2 random noise, a vector of length n times 2, because I want a vector for each of the 20 rows. I want a random value for each of the 20 rows, and that can be expressed as a vector with length n times 2, right? Because n is 10. So basically what this equation is doing is that it's generating some random data, some simulated data in one particular instance, right? If I wanted to repeatedly generate simulated data, what I would do is I would make sure that this subject adjustment is recomputed. This calculation is recomputed each single time, right? If this calculation is redone each time, then I get fresh simulated data each time. Here I've got one particular instance of the subject adjustment, which I just generated earlier. Okay, so where are we now? So what we do now is that we can replace the existing RT column in the SimDat data frame with our new RT column, right? So what we have achieved now is that this new RT column is now going to be able to include the assumption that we have one data point from subject 1 for subject relatives and one more data point from that same subject for object relatives, and the commonality between these two data points is that they're coming from the same subject, and that subject has a particular mean processing time that is included in the calculation, So if you're talking about subject 1, whatever the number for subject 1 is, that will determine the reading time of that subject for both subject and object relatives. So that's where the dependency is being now taken into account, that the data are dependent, the data for subject relative measurements and object relative measurements for a particular subject are now dependent. Why? Because we are including that subject's adjustment to the grand mean in the estimation of the or in the generation of the simulated reading time. Okay, now given such data, we can now analyze this, and in fact we must analyze it using a paired t-test or a linear mixed model or whatever, right? So in the paired t-test case, we would have RT as a function of condition. Condition here, I think in the data frame, remember that in the paired t-test, condition is actually this column here. So I'm sorry that I actually should not have used the word cond in this +-1 coding here, and as well as the word cond in the data frame. This is potentially confusing, and I'm very sorry that I didn't pay attention to this detail. In the next iteration of this course, I will fix this, and I will call this vector something different. It shouldn't have called it cond here, right? Because it's confusing now, because now you see this SROR, and here I just showed you -1 +1. But please remember that in the data frame we have factorial levels SROR, which have been some contrast coded. If you remember, I'd done that earlier. But that's not really relevant for the paired t-test, because the paired t-test has its own internal all I'm doing here is computing reading time as a function of condition, where condition is coded SROR, okay, in the data frame SIMDAT, and I've defined paired to be true, and I'm assuming that both variances are equal for the subject and object relative. And what I get as a result of this is some t-value and some p-value, etc., for the particular data that I generated just now. Okay, so when you run this code yourself at home, you might get some different numbers, or you will get different numbers, because you will get different random numbers that come out here, right? Okay, so remember that we can, I know I'm belaboring this point, and I know that you guys really know this very well, but I could have fit the same model using a linear mixed model. So Elmer RT as a function of condition with varying intercepts for subjects, right? And notice something that I'm doing here. I'm using this control parameter here in the Elmer function to just switch off all those convergence warnings, right? So now I'm not going to get any convergence warnings. This doesn't mean that there aren't any convergence warnings, but just for the purposes of explaining the important aspects of simulating data, I'm switching off the convergence warnings. And I'm going to just focus on the output of the linear mixed model. Okay, so this was a discussion we had earlier as well. So don't be upset about this. This is just for pedagogical reasons that I'm switching off the convergence warnings here. Okay, all right. So I have fit this model M1, and I can look at the output of this model, and I get, I get the same t-value that I got with the paired t-test, and I get the same difference between the means. Remember, because this is +-1 coded, the actual difference between the means will be 2 times this number. So 55.1 times 2, right? So, and that was in the t-test, we said 110.3, right? So that should work out. Anyway, so the point is that we've learned how to generate simulated within subjects data, taking into account the dependency between the subject and the object relative data points from each subject. And we know how to analyze the data using a t-test, paired t-test, or a linear mixed model with varying intercepts for subject, right? Okay, so the term one vertical bar subject in the linear mixed model call is actually referring to that by subject adjustment to the grand mean that we did when we generated the data, right? That's exactly what that term is estimating now. So in the model output, this term, also, why is this changing shape? That's weird. So this term 255 here, the standard deviation, is an estimate of the standard deviation that represents the variation of the by subject adjustments to the grand mean intercept, right? So remember that our true value was something like 300 or something. Wasn't it 300? Yeah, where is it? Here, right? Oh, sorry, it was 200, right? The subject adjustments value was 200. So the linear mixed model is coming pretty close to the true value. It's estimating it pretty accurately, right? So that's what this term is dealing with. It's trying to estimate that standard deviation that we had set up in the simulated data. Okay, so what do we do with all this? Now, why are we doing all this? We are doing all this because we want to compute power for this within subjects design. So the interesting thing is the way we will generate compute power is by generating this repeatedly with random data. So this will have to be freshly generated each time. New subject adjustments for each new simulation. Okay, and then each time we generate some simulated data, we can do a paired t-test or a linear mixed model. Either one works, right? So that's what I had done earlier. This is with some new generated data. I've got new numbers now, right? It will change every time, right? So here's the code for doing this, right? So I'm going to do 1000 simulations. I'm going to save the p-values, and I'm also going to save the t-values from Elmer. So that means I just created two vectors that have the length number of simulations, that is 1000, filled with empty cells, right? So I'm going to do 1000 runs of this for loop. Where is it? Yeah, this for loop will run right up to here. Okay, it will run for 1000 runs, and what it will do is each time this for loop runs, it will generate a fresh subject adjustment. Okay, and then it will create a vector, RT vector, that will be overwriting the RT column, you know, each time in the simulated data. And how will I generate this RT vector? I will do this piece of code that I just showed you a few minutes ago. Okay, so I've got a freshly generated subject adjustment, and I just write this piece of code to generate the simulated data, and then I do a paired t-test to compute the p-value and save it in the current in the relevant, you know, cell, and then I compute compute the t-value from Elmer and save it in the relevant cell, the ith cell of the t-vals Elmer vector. And so now what I can do with these two vectors, p-vals and t-vals, here is the following. I can compute the mean proportion of times that the p-value is less than 0.05 in the paired t-test, and I can also compute the mean proportion of times that the absolute t-value is greater than some criterion. Okay, so now the power estimate I get from the t-test is 0.085, so 8.5%, and the power estimate I get from Elmer is 12.4%. Now, why the discrepancy? The discrepancy occurs because I've set my criterion of the t-value at an absolute number of 2, right? I just decided that I will take 2 as my approximate ballpark, you know, for deciding on the critical t-value, right? Now I could have computed for the data points that I have 10 data points, right? For the 10 data points, I could compute the critical t-value, right? You remember all that stuff that we did in the beginning of the course. And if I now, instead of using 2, if I use the critical t-value for the data that I have, for the sample size that I have, then I would get exactly the same power that I got, estimate that I got from the t-test, right? So don't be confused by this slightly different power estimate in Elmer versus the power t-test. This comes from the way that I decided to treat the t-value as significant or not significant based on, you know, some cutoff like 2, right? The reason I'm mentioning this discrepancy is that you will often see in papers that people will say that, okay, they took 2, the absolute value 2, as their critical value for rejecting the null hypothesis in a linear mixed model. That's how people use a linear mixed model very often, right? My advice to you is to always do the chi-squared test using ANOVA. Okay, don't do this. Don't use the t-value as your criterion. The reason I'm saying this is that when the data have imbalance, then the t-value based test is not the same test as the ANOVA, and the ANOVA is the gold standard. That's the actual test for the null hypothesis. Okay, so that's the appropriate test for the null hypothesis. The t-value is just a kind of ballpark indicator in that case, and may not give you an accurate answer. Anyway, so I'm kind of digressing here. This is not the main point here. The main point here is to show you how to write a for loop to estimate power. Okay, in this simple case. All right, so now we're going to improve the sophistication level of our coding by automating this process a little bit, of automating the process of generating data, right? So we're going to write a function called within simdat. I'm sorry for the horrible name, but I couldn't think of anything better. But we basically will define in this function, just like we did for the between subjects case, the sample size. But remember that this is the sample size, the number of subjects in each condition. It's a within subject setup now. Okay, we will set up the intercept, the slope, the standard deviation of the residual, and the sigma, the standard deviation of the varying intercepts, right? So remember we had set up the subject adjustments there at 200. So these are just some defaults that I've set, okay, for the purposes of my demonstration. But you can now change these numbers to get different kinds of data, right? So anyway, so what I'm now doing here in this function is that first I generate the subject adjustments, which from now on I'm going to call U0. If you remember the linear mixed modeling lecture, I always wrote the subject adjustments to the intercept as U0. So that's why I'm writing U0 here, right? So these are the subject adjustments. The condition vector is the sum coded vector now, right? And the subject ID is going from 1 to 10 and has to repeat twice, if you remember the data frame I showed you earlier. And the reading time will be generated as follows. It will be the intercept plus the subject adjustments, right? Just like before, the slope times the condition coding plus random noise. Okay, and so what we do is we generate the simulated data, and then we create a data frame that has the subject vector, which we generated here, the condition vector, which we generated somewhere. Where did we generate this? Sorry, here, right? And then the RT vector, which we just generated here in this loop, right? And then we print out the simdat data frame. So this is a function that's going to produce simulated data within subjects data for us. Okay, so here we go. So how do we use this function? The way we use this function now is that we run 10,000 simulations, right? And what I'm doing here is I'm showing you how we can use this function to check whether the model, the linear mixed model, will be able to recover the parameters in repeated simulations. Remember, I discussed that earlier. So now we will see how the parameter recovery happens in the linear mixed model case, right? There are 4 parameters now. There's the intercept, slope, the standard deviation for the residual, and the standard deviation for the varying intercepts. Okay, so what I'm going to do is I'm going to create a parameters matrix that contains 4 columns, right? So 4 columns, and therefore I have to create a matrix that has 10,000 rows and 4 columns. So I created a vector with 10,000 times 4 empty cells, and then I created a matrix by specifying that I'm going to have 4 columns. So this command will create, this command will create a matrix that has 10,000 rows and 4 columns. Okay, so what I'm going to do is I'm going to fill the parameter values into each of the columns one by one, right? So here we go. I'm going to do 10,000 simulations. I first use my within subject simdat function with the default values. That's why there's nothing there, right? But you always have to put these parentheses when you have a function with some default values, right? You must always put the empty parentheses there, right? So this generates my simulated data because the function produces that data frame in the end, right? So I produce a simulated data frame each time in these 10,000 simulations. Then I use the Elmer function to do the data analysis, and notice that I've switched off all the convergence warnings, right? And so I get my model, and from my model I extract the intercept, the slope, the standard deviation, so the sigma, right, estimate, and the standard deviation of the subject by subject adjustments, right? So these are the 4 columns that I fill out row by row in the parameters matrix. And then what I can do is I can just look at the distribution of each of the columns, the intercept distributions, the slope distributions, the sigma distributions, and the standard deviation estimates of the by subject adjustments, and look to see why, if my model is on over these 10,000 simulations, is it able to largely recover the true parameter value. And you can notice that for beta 0, for the intercept, the model is doing a beautiful job. So most of the time in the 10,000 simulations, our intercept estimate is pretty close to the true value, right? That's this vertical line here, the true value. For the slope also, we're doing very well. We are able to estimate the true value most of the time around in these repeated simulations. The standard deviation is also pretty okay. Let me see, where is it gone? Here's the standard deviation. So there's the true value. I hope you can see this vertical bar here, right? This one. And we are landing near this ballpark in repeated values. Now the interesting thing to notice is the standard deviation estimate for the subject adjustments to the intercept. What you notice here is something interesting, that in a very large proportion of cases the estimate is 0. You see this here? For most of the other cases we are getting reasonable estimates which are near the true value, but there are many cases where the model is failing to estimate this thing. So what this is telling us is that we have too little data to get a good estimate of the sigma parameter. So let me just do this simulation slightly differently to show you what will happen if I were to increase my sample size big time. I should have put this in my slides, but it just occurred to me that this is a good exercise to do. So let me just find my function. So within subject, here's my function. So I have defined my function with some default values, and now I'm going to use this function here. So let me just copy this code and change some things here and show you what happens if I increase my sample size. Okay, so what I'm going to do is I'm going to change my sample size in this simulation. I'm going to change the sample size from n to, let's say, 1000. Okay, so I'm going to do 10,000 simulations, and it's going to take a few seconds, I guess. Oh, I could not find the function Elmer. That's because I didn't load it. Hello. Oh God, I don't know how to type, it seems. All right, so I think now this function, this for loop will run. It'll take a few seconds because I'm running 1000 data points each time. Okay, that's a lot of data each time. And so this loop is now running. To be a little patient. In the meantime, what I'm going to do is I'm going to just copy over the histogram, how I generated the histograms, right? So let's see how well the model does when we have 1000 data points as opposed to 10 data points, Okay, so maybe I'll pause the recording while. Okay, so we were at the point where I was showing you that if we increase sample size, under repeated sampling, under repeated generation of simulated data, the estimate for the by subject adjustments to the intercept will become much better centered around the true value. So you won't have this situation. If you have a large sample size while simulating data, you won't have a misestimation of 0 milliseconds standard deviation, as we are seeing here in this data set with only 10 data points. To demonstrate this point, what I did was I reran the simulation with a sample size of 1000 subjects. So this took me quite a lot of time to run, so I had paused the video so as to not waste your time, and I waited until the simulation finished. It took about 15-20 minutes actually. And then what I did was I plotted each of the parameter estimates, and this is what I want to show you now, right? So if you look at the intercept and the slope, we are again estimating these pretty accurately. We're getting pretty close to the true value now, right? So you look at the distribution, so it's between 700 and 750 or so. And what did we have in this distribution here? It's very hard to see the actual range, but one thing you can see is that we go a little bit further beyond 700, right? So it goes somewhere, this 400 is the lower bound, so something like 450 or something. So this is a much broader distribution. There's a lot more variation in the estimate of the intercept under repeated sampling. Okay, but if you increase sample size, you get much tighter estimates of the true value of the intercept. Same thing for the slope, and of course we get a good estimate of the sigma as well, right? Which was 300 was the true value, and we're mostly around that value in this. But what is most interesting to see here is the distribution of the standard deviation estimate for the bi-subjects adjustment to the intercept. And you see here that that under repeated sampling we get very good estimates of the true value, and this is happening because we have a large sample size. So the practical implication of this is that when you investigate the parameter recovery, given a data set that you had and some model that you're trying to fit, if you get a situation like this where you're misestimating a parameter, then what that is telling you is that you don't really have sufficient data to get an accurate estimate of that parameter, right? And so you have to consider whether you want that in your model or not, right? This is something you will have to think about and decide. So there's always some subjectivity in making this decision, and as I have mentioned, different people have different opinions. Douglas Bates would probably want to drop that parameter, but Barr et al. Would probably want to keep that parameter to be maximally conservative, right? So there's different opinions on this. All right, so where are we now? I think I've crossed over the so in this slide I'm just pointing out that the sigma u0 parameter is not estimated accurately, and I showed you under which conditions it would be estimated accurately if you had a larger sample size. Okay, so in my previous lecture on simulation, I had stopped at this point where I had shown you how you can recover or check whether your model can recover parameters in a fairly straightforward linear model. And so now what we're going to talk about, slide 49, is the situation where we have not one data point from each subject in each condition, in each of the two conditions, but multiple data points. So in the previous data set that we had generated, the simulated data, we had exactly one data point from each subject in each condition. So that's what this output is showing you, right? But in real life, when we are actually collecting data, what we typically do is that we have more than one data point for each condition from each subject. So for example, we might generate, or we might have 20 data points for each subject in subject relatives and 20 data points from each subject in object relatives. These multiple data points from each subject in each condition is going to be called a replicate. Okay, so the way we generate these replicates is the following. We're going to define the number of subjects, n is equal to 10, and then the number of replicates, k. In this case I've taken 20. You could take whatever number is reasonable for you in your context. And here again what I'm doing is I'm setting up the conditions vector as a sum coded vector, and this time I'm going to have each one of these levels be not n times in length but n times k, because each of the n subjects is going to deliver k data points. Therefore it's going to have to be each of these contrast codings will have to be n times k repetitions, right? Okay, and so the subject vector is going to look like this. It's going to go from 1 to n, but each of those numbers is going to have to be repeated k times, right? Because each subject is delivering k data points. So basically we are repeating each number id for each subject. And so once we've defined the condition vector and the subject vector, we can assemble the data frame, which looks like this now. So I have multiple instances of subject 1 with the same condition. That's because I have multiple replicates from that subject, right? Okay, so now once I have these multiple replicates from each subject, I can now generate repeated measures data in the following way. Okay, so what I'm going to do is I have my fixed effect intercept, right? So the grand mean intercept is 725, and I'm going to add to that, what am I going to add to that? The fixed effect of condition, right? So there was a 50 millisecond effect with the plus minus 1 coding. That means that we're going to have a 25 millisecond slope, right? And finally this is the simple linear model, and then we have the residual noise factor there, which is going to be which is going to have a mean of 0 and a standard deviation of 300. And what will be the length of this vector? So there are two conditions, subject and object relatives, and each of them is going to have n times k data points. So that's why I have n times k times 2 residual, the vector is of that length, right? All that I have not explained yet is this line here. Okay, so what I'm doing here is, first of all, I'm generating for each of the n subjects, I'm generating a random intercept. Okay, and then what I'm doing is, after having rounded these adjustments by subjects to the intercept, I'm replicating each one of these k times. Okay, so if I have subject 1, I'm going to have generated that subject's varying intercept adjustment. I'm going to have to repeat that k times. Why? Because I'm going to have k instances of subject 1. So I'm going to have to put the adjustment k times there. So that's why I've got a repetition here, and then I'm going to have to do that twice because I've done it once for subject relatives, or whichever coding this was, I've forgotten, and then I have to do it for the other condition as well. That's why I've got two rep commands here, because I first repeat the subject adjustment to take into account the replicates that I have from the subject, and then I do another repetition of the entire vector of subject adjustments with the replicates for the other condition as well. Okay, all right, so this on the surface, this piece of code here, this looks very challenging, but let me unpack it, so that it doesn't the complications become quite easy to see. So I'm going to now explain how this, I'm going to explain again how this vector comes about. Okay, just to be very clear about how this works. Okay, so let's break it up. Okay, first let's break it up into the smaller part where I've got the subject adjustments generated once. So I've got n subjects, so there's going to be n data points, and each of these numbers is going to reflect the subject adjustment to the intercept. Okay, this is the varying intercept here. So that's this is the vector u0, right? And so then what I'm going to do is I'm going to repeat each of the values in the u0 k times, right? So you see that 11 is repeated 20 times, minus 220 is repeated 20 times, and so on, right? So then what I'm going to do is that I'm going to now have how many 10 subjects and 20 replicates. So I'm going to have 200 data points for subject relatives, and then I'm going to have another 200 data points for object relatives. So I'm going to have to repeat that vector for the object relatives again, and that is going to give me 400 data points in total. And just as a sanity check, you can check that the dimensions of your data frame is actually 400 by 3. So that vector of data points, the subject adjustments will span the entire length of that data frame, right? Okay, and you can also check if you want to that each subject is delivering 20 data points in each condition, right? So what I'm going to do is, what I've done here, is that I've basically added a subject adjustment. This is what I showed you here, right? This is a very long command here, which I unpacked for you just now, which shows how I created a subject adjustment in this data frame in the vector for generating the reading times, okay, the simulated reading times. Okay, so now once we have the data in this form, what we can do is we can fit a linear mixed model with varying intercepts, for example, right? So we can start with a simple varying intercepts model. I've switched off all the warnings, as you can see, because I want to just focus on the simulation right now. Okay, so we can also fit a more complex varying intercepts and slopes model. That's what I've done. That's what I've done here, right? And when I do that, when I fit the varying intercepts and slopes model, I should get an output that's something like what you see on slide 59. Of course, your output will be different if you run this code yourself, right? It will look different. And so what you see in this code is, as usual, there is the fixed effects estimates with their standard errors and t-values, and there are the three variance components. Here's the intercept adjustment standard deviation, the slope adjustment standard deviation, and the residual standard deviation. Notice that the correlation between the intercepts and slopes is +1. So that means that there's a problem in estimating that parameter here, because that's an extreme value. And if you remember the linear mixed modeling lecture, this is an indication, a +1 or -1 correlation is an indication that the Elmer function is failing to estimate that correlation parameter. All right, so now what we can do is, until now I had only been adjusting the intercept, right, by subjects, right? So now what I'm going to do is I'm going to adjust the slope as well. That means I'm going to assume that some subjects have larger relative clause effects and some have smaller effects, okay? So we have seen that kind of model before. So I'm going to assume that subjects have the standard deviation of the varying slopes is going to be 50 milliseconds, okay? So I've just chosen 50 arbitrarily just for illustration purposes. There's nothing deep there, right? So I'm going to create a vector u1 which now represents my slope adjustments. So this slope adjustment, these are 10 subjects, 1 2 3 4 5 6 7 8 9 10, right? So the first subject that I've randomly generated the slope for has a slope that is larger than the average slope. This third subject has a slope that is smaller than the average slope, and so on, right? So these numbers will vary each time I simulate data, because I'm simulating getting new subjects, and every subject is going to be different, right? That's the reason that these numbers will differ. Okay, so now I've got the slope adjustment. So the way that the slope adjustment will go into simulating data is that when I have the slope term, which is 25, if you remember in our model, when we generate simulated data, we've got the slope at 25 and we multiply it with +1 or -1, right? So that's the average slope, ignoring the individual variation. So now what we are adding in this line here is that what we are adding is the slope adjustment to the fixed effect slope, and I'm putting it in brackets because I'm going to multiply both these terms with +1, which is one of the relative clause levels, right? So what I'm doing here is, for object relatives which are coded as +1, I can now generate, having generated random adjustments to the slope, I can take the fixed effect value 25 and the random adjustments to the slope for the 10 subjects and generate the varying slopes for the subjects in this particular instance, right? So I've got the first subject has a very large slope. That means the object relative has a positive. That means object relative is slower than a subject relative, and here I've got a negative slope, right? So it's the opposite pattern. That means that different subjects are going to have different effects now, right? And so, am I saying this correctly? This is the, so actually I should be looking at the differences. What am I doing here? Yeah, sure, right. Sorry, I was correct here. So what's happening here is that this is a positive adjustment to the average effect. So it's larger than average, you know, and this one is smaller than average, right? And so on. The negative ones are smaller than average, right? Okay, so basically now we can also plot this by subject variability, right? In the mean subject relative between the subject and object relative effects, you know, so that every subject is going to have a different effect for subject and object relatives, right? So what I've just, this is only for illustration. We are never going to publish such a plot, or we are never going to display it in a paper or anything like that. This is only for you to notice that, for example, the subject the subject relative clause value for this subject is this one here, and the object relative clause value is here, right? So the different subjects have different effects for the subject and object relatives. That's the variability that is induced over this fixed effect. So if we did not have any varying slopes, then all subjects would be assumed to have the same slope of 25 milliseconds. So this varying slopes is adding variability in this estimate. Okay, so now that we can generate different slopes for different subjects, we can now incorporate that into the simulation, right? And just into simulating data. So the way I'm going to now simulate data is that I'm just going to add one more thing into my simulation line, right? So I had earlier, what I had was the fixed effect 725, the subject adjustment, right? I explained this extensively just now, right, to the intercept. And earlier I had only 25 here. This was just the number 25 multiplied with +1 or -1, right? And then the residual standard deviation, the residual error, right? So the only innovation now is that I have, instead of writing 25 here, I'm going to write, oh gosh, here. Instead of writing 25 here, I'm going to adjust 25 by subject. And I'm going to do it exactly the same way as I adjusted the intercept, except that I have a different standard deviation of 50, right? Remember, I set up the varying slopes to have a smaller standard deviation. So what I'm going to do now is I'm going to generate data for n subjects from this normal distribution, and then I'm going to repeat each one of those numbers k times, and then I'm going to repeat the entire vector twice, one more time, right? So that I have the vector for subject and object relatives. And that's it. Now I can generate data that actually has varying intercepts and slopes, right? So one thing I want to show you here that is very important is to learn how to visualize the bi-subject effects, right? So one way to visualize them is by using a function like this ggxy plot that I've written here. You can download it and look at it later, and you will encounter it again in the homework assignments. Okay, what this function is showing you is that for the 10 subjects, I'm displaying these subjects, in this case simulated data, but I'm displaying the subject, each participant's subject and object relative clause data, and I just fit a linear model on each subject's data. And what this what purpose this serves is that it allows us to visually check how much variability there is in the subject object relative clause effect between subjects, right? what we are seeing here is that some subjects have a slope going down this way and some subjects have a slope going this way. So there's quite a bit of variation in the slope here, right? That's what that 50 millisecond effect is inducing, right? So every subject has a different slope. The x-axis is slightly misleading here. I'm sorry, I should have fixed this. It should have been just -1 and +1. These numbers are not relevant here, right? Because this is just a +1 -1 coding. There's nothing in between. And on the y-axis is reading time, and so you can see that there is some variability here, right? So we can now fit a model to the simulated data, right? And we can fit a model with varying intercepts and slopes. Notice that I'm not assuming any correlation here, because earlier I already realized that that was not a good idea because I was getting a +1 correlation, so I just dropped it, right? So now I don't have any correlation parameter here, as you can see, and everything else is pretty similar. Of course, I have different numbers here, and the reason for that is that I have generated new data. Every time I generate data, I'll get different numbers. When you rerun this code yourself, you will find that you will get different numbers than me, obviously, right? You're generating your own data now. Okay, so this model that we have just written up can be written like this. We can say that our reading time is generated from a normal distribution with some intercept, fixed effect intercept, some intercept adjustment by subjects, and some fixed effect slope beta1 with some adjustment u1, right, to the slope. This whole term has to be multiplied with the condition coding to get the +1 -1 coding to ensure that you get the correct simulated data for each condition. And this is the residual standard deviation, right? This is one way to write the model, okay? And these are the two variance components in addition to the residual standard deviation, okay? So these are 3 standard deviations that we will be estimating in the model, and you saw that here, right? We've estimated 3 standard deviations: the intercept adjustment to by subjects, the slope adjustment by subjects, and the residual error. Okay, so now where was I? Right, so I just said that there are 3 variance components, and these I just explained to you, right? So I'm not going to repeat this. I'm just pointing out what the 3 variance components are, okay? All right, so now I want to show you a more sophisticated approach for generating generating the data, generating the random effects, basically, right? So the way that we have been doing it right now is that we've been using this rep command repeatedly, if you remember. You know, it's kind of it's okay, there's nothing wrong with it, but it's a bit ugly, right? This rep command is could be improved on a little bit, okay? So I'm going to show you a little bit a slightly better method for generating the random slopes and also intercepts, actually. Okay, so let's see, where are we? Right, so this is where we're at. So what we're going to do now is that let's say we have 10 subjects and 20 replicates, right? And so we're going to do the usual thing that I've already shown you. This is not new. I'm going to generate my condition vector and generate my data frame with the subjects set up correctly and the condition vector set up correctly, okay? So now I'm going to add to this data frame. I'm going to add the simulated data in the following way, okay? So first I'm going to generate a data frame. I'm going to generate a matrix called the which I will call the U matrix, okay? Small u, small case u. I'm going to generate a U matrix that's going to contain the intercept adjustments in the first column and the slope adjustments in the second column. So what I'm going to do is, if I have 10 subjects, I'm going to have 10 rows in this U matrix. The first column will have the intercept adjustments, the second column will have the slope adjustments. Okay, so that's what I've done here. What I've done is I have set up the standard deviations for the intercept and slope adjustments, 250, right? And then I created a subject vector going from 1 to 10 in this case, and I created a column called U0 that has the intercept adjustments, which I've just generated here, and another column called U1, which contains the slope adjustments. Okay, so this U matrix is now going to contain the intercept and slope adjustments. Now, the reason I've created this U matrix now is that I can look it up. I can look up the U matrix. When I want to know subject 1's intercept and slope adjustment, I just look up this U matrix, look at the first row which contains the first subject's data, and use the intercept and slope adjustment in my data generation function, for generating simulated data. So how do I do this? Let's do this. Take a look at this. This is what my U matrix is going to look like. The first column tells me which subject I'm talking about, and the two columns tell me the intercept and slope adjustments for that particular subject. Okay, so what we're going to do is that for each row in the simulated data frame, the SimDat data frame, we're going to look up the subject ID in each row, and when we're going to find out from the U matrix what the intercept adjustment is, and we're going to find out from the U matrix what the slope adjustment is for that subject, right? And then we're going to plug in that value, the U0 and U1 value for that subject, into our data generation function for the particular row in the data frame. So what that means is we're going to go row by row. Where am I? Sorry, where is it? SimDat is here. I'm going to go to the first row, look up subject 1. Subject 1's intercept and slope adjustment can be found in the U matrix, right? In this U matrix, here it is, right? 83 and 26, and I'm going to use that to plug into this command and write a random value, the random simulated value for that subject in that row of the data frame. That's basically it, right? The rest is now technical details. I'm going to show you how this works, right? So let me make this a little bit bigger. So we begin here. What I've done is I've set up the number of rows in my simulated data frame, right? And then what I've done is I've created an RT vector which has as many empty cells as there are rows. So I'm going to fill in this RT vector row by row, okay? And so then what I do is I set up my fixed effect intercept and my slope here, and my residual standard deviation. These are my fixed values that I will use for generating the simulated data. Then I'm going to go row by row as follows. Okay, so for every row I'm going to take the beta 0 value, which is 725, and add to it the value in the U matrix so that's the column in the U matrix that corresponds to the ith row in the SimDat data frame, right? So this command here, SimDat I with a comma after that, is isolating the ith row of the SimDat data frame, and then this command here, the $subj command, is looking up the subject ID. So this entire command is going to serve the purpose of giving me a number, which is the row of the U matrix, right? So if this number is, for example, 1, what that tells me is that I'm looking for the first row of the U matrix, and I'm looking at the U0 value in the first row of the U matrix. What's the U0 value in the first row of the U matrix? That's this number 83, right? So that tells me the intercept adjustment for this subject here. Now it just happens that the first row, where is it? The first row of the U matrix happens to be the first subject's data. That's how I set it up. Okay, all right. So the same thing happens here. I look up the subject ID for the ith row of the SimDat data frame, and I'll get a number here which tells me which row in the U matrix to look at, and then I just look up the U1 value, which is this one here for the first row, right? 26. So that's the number that I'm going to plug in, right, dynamically as I go through this for loop. I'm going to keep adding intercept and slope adjustments by subjects. So this is a very general way to add intercept and slope adjustments into your simulated data, right? So when you're generating data with intercepts and slope adjustments, right? So the big development here, I've already explained it, so I'm not going to belabor this point now. I'm just spelling out in these slides here exactly how I produced those simulated data here. Okay, so you can look at these slides yourself and ask me if you have any questions. I think I explained this just now, right? All right, so this is all straightforward now since I've explained this. Okay, so basically that's the situation, that's the place where we are at now, right? What we have is that you can now generate data that has varying intercepts and varying slopes, right? And of course you can also check whether your parameters can be recovered by the model. That's something you can do yourself to see if it works. Okay, so continuing with this lecture on generating simulated data for within subjects designs. We've reached the point where we can produce data with varying intercepts and slopes specifications, right? And so once we have generated such simulated data, we can fit the same model as M3 that I had shown you earlier with varying intercepts and slopes with no correlation between the intercepts and slopes, right? But this time we have a parameter specifying the true value of the slope adjustment standard deviation, right? So what we will do is we will repeatedly generate simulated data. Then we will fit the model with varying intercepts and slopes, no correlation, so the double vertical bar, and then print out the summary from the model and check whether the model parameters roughly match the true numbers that you use to generate the data. That's the sanity check, checking whether parameter recovery happens or not under repeated sampling. But we can also use this for doing power calculations now. Okay, so this is getting closer to the true way, the correct way to do power calculations. Okay, we're getting closer and closer now. So what I want you to do now is to write a function called gendat that generates data, which takes as input the sample size for each subject, the number of replicates, the intercept and slope fixed values, and the three variance components for the intercept, slope, and the standard deviation. So you just write a function that will produce simulated data using the code that I've shown you earlier. Okay, so you just have to assemble the code now from the little pieces that I've shown you, and the output should be like this. Like when you give it some values like 5 subjects, 5 replicates, some values for these, and you should get simulated data that looks like this now, right? There'll be a subject column, condition column, and RT column. So notice that I didn't give any condition values here. That should be inside the function just for the 2 condition case right now. This is not a very general function. It's just for the 2 condition case, right? Okay, so once you have written such a gendat function, you should write a for loop with, let's say, 100 iterations that computes the proportion of times that the absolute value of the t-score for the slope is greater than, let's say, 2, right? Just take that as a critical value. So this is going to be the estimated power of the experiment approximately, and this would be the probability of detecting the effect given that it's true, right? So the true effect is 25 milliseconds, or rather actually 50 milliseconds. The slope is 25 milliseconds in the plus minus 1 coding. So the proportion of times that we would detect that significant effect will be the power, right? So that's something you should do. Okay, give it a shot, because I've shown you all the little pieces that you need to do all this, but you can now write this for loop. And what I say here is that you should use the, sorry, did I say t-test? I did not mean t-test. I said this t-score for the slope from the linear mix model is what you should use in this case to check whether you get a significant effect or not, right? So because we have completely balanced data, the t-test score from the linear mix model will be exactly identical to the result that you get from the ANOVA. That's why we can just use the t-test score here. In general, I would recommend that you use the ANOVA function in case you have imbalance in your data when you're doing data analysis. But in this simulation code, the simulated data is perfectly balanced. There's absolutely no missing data at all. So therefore, it's fine to use the t-test value from the linear mix model to compute the power. Okay, so that's what you should try out. And the next topic that I will cover now is how to generate data with correlated intercepts and slopes. Okay, so the way we will generate correlated data is that we will have to use the bivariate distribution, right, which I have discussed already in the course. So the way we will do this is that we will use a library mass and generate a variance covariance matrix and use that variance covariance matrix and the multivariate R norm distribution from the mass library to generate certain number of subjects data. So in this case 50 subjects data, such that the intercepts and slopes are both coming from a normal distribution with mean 0, and the variance covariance matrix determines the standard deviation between standard deviation of the intercepts and the slopes, right? So the standard deviation of the intercept is 200 and that of the slope is 50, and some correlation, and that correlation is defined in the off diagonals as 0.5 here. I've just taken 0.5 as an example. So this MVR norm function is going to generate bivariate data now, right? That will be correlated. We will have correlation 0.5. Okay. So how does this work? I can look at, so when I generate this bivariate data and save it in this matrix U, what I'm getting is 50 rows, and the first column is the intercept adjustments and the second column is the slope adjustments, right? And the correlation 0.5 you can visualize by plotting this pairwise in a plot, right? So this is the U0 matrix, this is the the U0 vector, the U1 vector, and you can see a positive correlation here which is about 0.5. If I had set this correlation to 0.9, I would get an even tighter correlation here. Okay, maybe I should do this. Let me just do this now. Oh no, sorry, this is here, right? Right, so here it is. I have my library. So I've generated this correlation, this matrix here. If I look at the plot, I see that the, I should redo this. Right, so we see this positive correlation here. It's pretty noisy, but you can still see it. But if I change this to 0.9, right, much higher correlation here, what's going to happen is that if I look at the correlation plot again, I'll see a much tighter correlation here, right? So this correlation parameter actually is being specified by us as the gold standard parameter, you know, that we are using for generating the simulated data, right? Just like we used the standard deviations of 300 for the sigma, 200 for the intercept, and 50 for the slope. We are adding one more parameter, which is the correlation, and we are specifying what that correlation is going to be for generating simulated data. All right, so if you had assumed that the correlation was minus 0.5, right, then you would write minus 0.5 here, and then you would get negative correlation here. Okay. All right. So, and if you specified the correlation to be 0, then you could generate exactly the same type of data as we generated with the double bar syntax earlier, where we had two independent intercept and slope generations of for each subject using the rnorm function, right? So this mvrnorm function can generate the same type of data as the two independent rnorm functions if you set the correlation to 0. Okay, it's an important point. And so if the correlation is 0, now you will see basically no association between the intercept and slope anymore. You can't really see this very well here. Look, there's a lot of variability, and that's because we have very sparse data here. We have only 50 subjects data, I think, right? 50 data points. Okay. So what I just showed you is the way that you can generate correlated intercepts and slopes using the mvrnorm function. And so what you now need to do is you need to extend your gendat function to generate correlated intercepts and slopes by using this code that I've shown you, right? You're going to have to define a variance covariance matrix that has so let me show you what this looks like. Right, so if you look at the sigma here, so let's just, if you look at the variance covariance matrix here, what we have is on the diagonals you have the variances, that means the sigma squared for the intercept adjustment and the slope adjustment. Okay, on the off diagonal you have something called the covariance, which is the two standard deviations for the intercept and the slope multiplied with the correlation. That is the definition of covariance. Okay, and so on both the off diagonals you are seeing the covariance here, right? The two standard deviations, intercept and slope standard deviations multiplied with the correlation gives you the covariance, and that's this value here. So this is this matrix, this variance covariance matrix is what goes into the generation of bivariate data, right, that has some correlation with each other. That's just how multivariate data is generated. Okay, right, so you should now be able to extend your gendat function to generate correlated intercept and slopes, right, and then compute power using this function, right, and then you can check whether the parameters are recovered under repeated sampling and so on, right? So all this will be part of the homework assignment for you. So I will give you some practice in doing this, and I will help you in producing this code step by step, okay, in the homework assignment. So that's it. That's the whole lecture on generating simulated data. What is missing right now is generating more realistic data in the Latin square design, right? That is something I will talk about in the next week's lecture. We are now at the point where we can generate reasonably realistic repeated measures data, and we can compute power with it, but we are still short of the final step where we can produce Latin square designs. Okay, but we will come to that later after we've had some practice with this setup that I have taught you. So that's it for this lecture then on simulation, at least for this week.